Hello students, welcome to this course on signals and systems. Today's lecture is all about introduction for signals, and we will also discuss some real world examples related to signals, and we will also see certain classifications on signal, the basic classification of the signal with respect to the independent variable that it is depending upon. Okay, let us actually see all these terms and the terminology related to this particular course in this session. Before starting this particular course, I would like to just let you know about the introduction um, and why actually we are forced to learn this particular course in this particular semester. In this modern age of our microelectronics, signals and systems actually play a vital role. It is a very important subject with many applications in the areas of science, technology, where where we actually deal with many kinds of circuit designs um, and earth sciences such as seismography and all, and the communications in all types of communications that what we establish either through satellite or either through this different branches of communications such as analog communications or digital communications that we deal with, and the biomedical engineering in today's world, and energy generation and distribution, speech processing, image processing, video processing, whatever this, etc. Any field that what any area that what we generally deal with today, where the signals and systems actually will be a backbone for them. Therefore, it is essential that every engineer like us should have a thorough knowledge on this particular subject. Understanding and signals and systems also must help us to study some other parts of the courses in coming semesters, and such as your signal processing or control systems or analog or digital communications. And similarly, today, as said, we shall start with what is meant by signal. Hope that this is audible and it is clearly visible. A signal may be a function of time, temperature, or position, or pressure, distance, anything. Okay, anything, something like that. Actually, some signals in our daily life that what we see and hear, uh, such as music, speech that I deliver, as well as the pictures that you see and the video signals that you see now, they are all considered to be signals. And systematically, we can also define particular signal, a signal, as a physical quantity. Okay, so might be a physical quantity, or in a mathematical sense, it can be defined as a function of signal can be defined as a function of one or more independent variables. Function of one or more independent variables. And essentially, a signal should contain some information. Okay, it is a function which carries some information. Signal is a function which carries some information. So this is the prime difference between your mathematical functions as well as the signals. Signal is also a function which carries some information. All the signals are functions, but all functions are not signals. You need to understand this point clearly. And in electrical sense, the signal can be a voltage signal or a current signal that what you see as an input to many circuits, electrical circuits. And similarly, the voltage or currents, it is a function of time as an independent variable. Here the physical quantities that I'm saying as they are the voltage or the current, and they are depending upon some independent variable like time. We write it as V of t or I of t or something like that. In daily life also, we come across different kinds of signals such as electrical signals or the radio signals, TV signals, the computer signals, etc. All these signals that we come across are naturally generated signals. Most of them are naturally generated. However, there are some signals which are also generated in the laboratory synthetically. And such kind of signals I call them as synthetic signals, which are generated uh, in the laboratory. Okay, I would like to just represent the physical interpretation and the representation of a signal. As I said, in a two-dimensional way, generally we say, okay, generally we represent the functions with respect to the independent variables. Let us consider the independent variable as x, and the function defined on that independent variable is represented with respect to the y-axis. And the change in this function with respect to the independent variable x, we generally call it as the representation of the change of f of x with respect to the independent variable x. We call that it as the waveform. Okay, it might vary with respect to x. For different values of x, generally this f of x may vary with respect to x. It might take different shapes. It might take different shapes whenever we are trying to represent with respect to different kinds of values with respect to this x. Therefore, function is always dependent upon the independent variable x. Okay, and the functions can also be defined with respect to its dimensions based upon the number of independent variables it is depending upon. Okay, so let us consider when a function depends upon a single independent variable like x, then I call this f of x as a one-dimensional signal. Then this is called as a one-dimensional signal. And if the signal depends, if this function depends upon more than one independent variable, then generally we call that it as a multi-dimensional signal. We call them as when f. So let us consider if f of x is varying only with respect to x as f of x is equal to x square, then this particular signal or a function which is dependent upon x, which is represented as x square, I call this as a one-dimensional signal. If that particular function depends upon one or more independent variables like f of x, y, and z, and where this function is now written as f of x comma y comma z is written as xy plus yz plus z square. The function on these three variables are represented something like this. And if this variation of f with respect to all these three variables are plotted something like this, then it becomes a three-dimensional signal. Okay, so the dimensions are nothing but the function, the number of independent variables on which your function is depending upon. And definitely all the signals should hold the properties of the mathematical functions that what we observe. Okay, generally I think you know about functions, the mathematical functions. Okay, and I would like to just speak about some examples, real world examples, which vary actually with respect to some independent variables. Let us consider a image signal. Okay, first of all, I would like to talk about a one-dimensional signal, which actually can be represented with respect to a single variable. Let us consider a speech signal. The speech signal, the intensity of my voice actually depend upon time. Okay, the variation of my vocal cords, which is actually delivering some speech, is represented. The intensity is generally represented with respect to time, and that particular speech signal now can be considered as a one-dimensional signal. Similarly, a picture or a photograph that what we generally see can be considered as a two-dimensional signal, because the photograph generally depends upon two variables like, okay, let us consider, okay, it is not depending upon a it depends upon two variables such as x and y, okay, where they are the spatial coordinates. Okay, they depend upon two coordinates. Okay, this f, the function is depends upon x comma y. Okay, I'll just try to show you. The picture is placed on a coordinate axis. Okay, coordinate axis which has some two variables. Okay, where it is continuously changing with respect to x and y. Okay, so whenever you consider your photograph, spatial coordinates that it depends upon two variables, that is x and the y coordinate. Any particular small of your image, which is called as a pel or a pixel, the smallest component, okay, with equal sizes which your picture is divided, we call them as pel or pixels, and that pixel actually depends on, it is represented with respect to this particular function f of x comma y. The f of x comma y represents the brightness levels or the intensity levels with respect to that pixel. Since it depends upon two spatial coordinates like x and y, now your image is called as a two-dimensional signal because it depends upon two spatial coordinates. Similarly, consider a video signal or a motion picture. In addition to this, because a motion picture is a moving picture, with respect to it not only depends upon the spatial coordinates, therefore it also depends upon another variable like time, since they are moving with respect to time. Therefore, the motion pictures or the video signals are three-dimensional signals in nature because they depend upon three independent variables like x, y, which are the spatial coordinates, and the other third variable is the time. Okay, these are different kinds of examples that is related to the signals. I hope that now you understand what is the primary difference between the mathematical functions and the signals that what we generally try to study here. And coming to the other parts, I have also said about what is meant by a waveform. It is a pictorial representation of that signal variation with respect to that independent variable. And we have also defined what is meant by the dimensions of a signal. And the dimensions are directly related to the number of independent variables your function is depending upon or the signal is depending upon. Okay, we have also discussed about some real world examples in this particular video. Okay, and thank you for listening. If you have any doubts, you can ask me now.